Okay. Our next speaker is Dr. Ani Kembhavi. Dr. Kembhavi is a researcher at the Allen Institute for the Artificial Intelligence, the AI2, which was established by Paul Allen, one of the founders of Microsoft. Dr. Kembhavi deals with computer vision and artificial intelligence and has developed systems for large machine learning at Microsoft in the past. The topic of Dr. Kembhavi's today addresses the question, may I have your attention please, said one neuron to the other.
I'm sorry for the delay. We're trying to set up a demo. But I think I'll start with the talk and then hopefully the demo will figure itself out. So my name is Ani Kembhavi. I work at the Allen Institute for AI in Seattle in the US. And today I'm going to tell you a little bit about our work on understanding visual illustrations. And towards the end of the talk, I'll spend a couple of minutes telling you about some work by my colleagues at AI2 on understanding natural images. And if the demo figures itself out, I'll hopefully show you a live demo. Okay, so the world of visual illustrations is very large, very rich, and very diverse. I've just shown you a few cases here. There's science diagrams, there's maps, physical maps, political maps, 3D visualizations, infographics, and the list is endless. So why do we find these visual illustrations interesting to work on? Most computer vision researchers, in fact, focus on natural images, and only recently there has been a bit of research on visual illustrations. A lot of knowledge in the world is stored in the form of visual illustrations. And capturing this knowledge and understanding this knowledge requires us to understand these modalities. But there's a second reason that's quite interesting. You see, visual illustrations are purposefully designed by humans. And so they're designed to suppress background clutter more so than natural images. However, they're very dense and rich in information. And so they serve as a fantastic playground for visual and textual reasoning. Here's a simple example of an image. It's a very simple science diagram that most of us might have studied in middle school. A natural image might have, you might see a tiger, or you might see a tiger eating a deer, or so on. But this diagram actually captures the food web of an entire forest. And so now you can start answering questions and reasoning, such as a simple question like, which animal does the bobcat eat? But then you could also answer higher order questions requiring higher order reasoning. For example, if the population of squirrel died out, what happens to bobcat? And so now you have to understand who eats whom, and what does eat mean, and what happens to populations when food reduces. So as I said, the world of visual illustrations is very large and diverse. So where does one even start trying to understand them? Well, we see two problems in this field. One is syntactic parsing, and one is semantic interpretation. So syntactic parsing is the part where you like to detect all the objects, you'd like to detect their relationships with the background, you want to detect relationships with one another, and so on. And semantic interpretation is actually grounding these syntactic detections in some semantic space. So here's a simple example. Let's take a very, very simple object like an arrow. In the top image, the arrow signifies motion. The moon is rotating around the earth. In the second image, arrow signifies consumption. But the third image, arrow signifies phase change. And so as you can see, a simple element like an arrow could mean very different things. And so, which is why semantic interpretation is important. So in this talk, I'll talk a little bit about different works that we've done towards syntactic parsing, as well as semantic interpretation. We haven't yet worked on explicit semantic interpretation, but we study semantic interpretation in the context of question answering. So there's been a lot of work from the visual graphics community on understanding visual illustrations. And so we build upon one such representation called the language of graphics. There's actually, this work is quite large and quite interesting, but I've simplified it to a great deal in this diagram. Essentially, you can think of an illustration as a composite graphic. It has a graphic space. This space could just be white, but in fact, the space might actually be meaningful. So the locations of objects in this space might have some semantic understand the type of graphic space. You want to be able to understand what are the constituents, which are the nodes in this graph. You want to understand relationships, which are two kinds of relationships. One are relationships between nodes, which I call inter-constituent relationships, as relationships between the nodes and the background. So the way we proceed in this problem is to run classical computer vision algorithms to detect constituents, to detect relationships, and then tune these algorithms to extremely high recall, such that you now have bags of constituents and bags of relationships. And then you want a higher order model that picks elements from these bags and constructs your diagram parse graph. I failed to mention that much like language does parse trees, diagrams, we have the notion of parse graphs. So I won't go into details here. You can look it up in our papers. But for constituents, you can think of this is basically an object detection problem. And so people have employed these successfully in natural images, and they also work pretty well on diagrams. So you have convolutional neural networks detecting constituents. Then you have a number of machine learning classifiers, including random forests that we use to take pairs and triplets of these constituents, look at their positions with respect to each other, look at their positions with respect to the background space, and start getting relationships extracted from the diagram. Similarly, you can do constituent space relationships using things like kernel density estimates, which can tell you usual locations of elements based on their semantic interpretation. And so now what you have is bags of these constituents and relationships. And you want to start picking elements one by one from this bag and sequentially forming your diagram parse graph. So for this, we proposed a deep sequential diagram parser. So this model is quite simple. In the middle is the meat of the model. It's a 2-layer LSTM, which is, like I said, the meat of the model. Candidate relationships and constituents are fed in from the bottom. And so each relationship is now encoded with a feature vector, which says what kind of relationship it is, what is the probability of detection, where it is, and its relationship to other relationships in the diagram. And so the job of this sequential parser is either to accept or reject a candidate relationship. And so you can see on the top of the image, you start adding nodes in the graphs and edges in the graph. So what does this sequential parser actually learn? Well, it learns things like if A is connected to B and B is connected to C, and you have another element D which is in the same location with the same Y coordinate, well, this might be a linear chain, and linear chains are common in diagrams. Or for example, if A, B, C, D form a link and E would complete a circle, then this is the kind of relationship that I want to accept, and I want to reject relationships that might cut the circle in half. And so looking at your training data, your parser can learn common configurations, common relationship tuples that exist in a diagram, and then construct this diagram parse graph. Here are some qualitative results on what it does. So for example, the first column shows you food webs, and so the parse graph is able to extract nodes and edges, and here edges are basically connections between arrows and animals. Relationships are also labeling type, where you have text boxes and you want to figure out which text box relates with which object drawn in the diagram. The second case is an example where it has correctly found out that there's a cycle here. These are phases of the moon around the Earth. The third is a parts of diagram, so it's detected that there's just one object and all the text boxes are actually telling you different parts of the object, and so on and so forth. So what I've told you so far is how to take a complete diagram and then sort of break it down into this diagram parse graph. But another interesting thing is to actually do fine-grained analysis. Now, if you want to do fine-grained analysis, for example, you want to understand parts of these diagrams. How would you do it? Well, one way to do it is to get a lot of training data with lots of object categories and get humans or crowdsourcing workers to annotate different parts. The problem is that training data is expensive, as we all know, and more so in the space of diagrams, it's very scarce. And so this motivated a project that we recently worked on, which was matching between source and target images in a one-shot scenario. The reason I call it one-shot is that the problem is where you have a source image. So for example, an image of a bird with n parts, n points with their part labels. And then you have a target image, which might have different appearance, different pose, etc. And you want to transfer these labels from left to right. But the key thing here is that you've never seen an image from this category in training. And so maybe you've trained on cars and buses and motorcycles, and you want to be able to do this on animals. And so why is this a challenging problem? Well, first of all, as I said, it's a one-shot scenario, and so you must generalize to unseen categories. Second of all, diagrams are quite interesting because they don't have any background clutter, so that's good, but they also don't have any color or texture, so that makes it hard for convolutional neural networks to work. This also makes local appearance cues extremely ambiguous. For example, you might have a point and you only have white space there, so there's no appearance information at all. And so you want to be able to grow your region so that you can get some context from surrounding regions. Thirdly, there's pose variations, so absolute positions of these pixels may or may not be useful. And fourth of all, you want to enforce a one-to-one matching. So what was our approach to this problem? So this, we have what we call a structured set matching network. And so there's two parts of this problem. One is an appearance matching network, and the second part is a structured prediction model which we build on top of this network. So let's start with the matching network. You have the source image on the left, and you have the target image on top. The source image contains endpoints, as does the target image. The source image has these labeled, and you want to transfer these to the target image. So now what you do is you extract an image patch around each point, and you pass it through your encoder network, which is a convolutional neural network. And so now you end up with n embeddings from the source and n embeddings from the target. One trick that helped us a lot, which we borrowed from the original matching networks paper, was to contextualize these embeddings. And so instead of having these embeddings extracted independently, what you want to do is within each image, you want to provide a little bit of context by passing these through something like an LSTM. And so an LSTM, mind you, needs to be bidirectional because you want context to flow from every point to every other point, makes your features a little bit more robust. And so now you have an n and by n problem. And so you want to use passes through some sort of a similarity network, which is you have n embeddings and from the source, n embeddings from the target, and you want to come up with n square similarity numbers. And so the vanilla way of doing this is to say, well, I'll just take a dot product. And there's fancier ways to do it as well. That's not, you can read that in the paper. And so now you have these n square similarity measures, and now you want to be able to transfer these labels. So how do we do that? For that, we use a structured prediction model, which has 4 factors. So on the bottom left, you'll see appearance similarity. This is exactly what we have from the appearance matching network. You want to be able to match 2 parts that look similar to each other. The second thing is part appearance. So even though this is a one-shot scenario, well, you may have never, you will never have seen this category before, but you might have seen the part before. So for example, maybe in your training data set you had tigers, but in your test data set you had chickens. And so both of them do have heads. And so the positions of, the appearances of heads might provide some cue between source and target. Interestingly, our experiments found that this doesn't help too much. It helps a little bit because, tigers' heads and chickens' heads actually look pretty different. Third, you have what we call global consistency. So it is 2 parts, structural and appearance consistency. Now, think of the images that I showed you before. So you have, a bird on the source and a bird on the target, and one bird is looking this way and the other bird is looking the other way. And so if you use absolute positions, you're not going to be able to transfer any sort of parts. If you use, if you normalize them by the size of the image, by the length and width and height or whatever, it still doesn't help you. But what you want to be able to be consistent about is that on the left side, if head is always on the left of the neck and neck is always on the left of the torso and torso is always on the left of the foot, on the right side, if one is on the right of the other, then the other should also be on the right. So you see, you can have some sort of affine transformation, and you want to be consistent in this affine transformation across all pairs of images. Similarly, you also want to do this in appearance space. For example, if point A is, has more texture than point B, which has more texture than point C, then A prime should have more texture than B prime, should have more texture than C prime. And so you want to be able to be consistent between your source and targets, which is where this factor comes in. And lastly, of course, you want to have a matching constraint. So you want to have a hard constraint which says that There's always a one-to-one correspondence between your source and target. And so when you run this structured prediction model using approximate beam search inference, it actually does pretty well. Here are the kinds of label transfers that have done well, and there's of course some examples that we have which do not do very well because they have just way too much pose and appearance difference. Okay, so I'm going to switch modes a little bit and say, okay, so we're starting to work on syntactic parsing. How do we actually interpret these semantically, and how do we actually answer questions? So let me give you a quick 30-second overview of how do people actually answer questions about images. Well, here's a vanilla architecture that people use in the super hot field these days called visual question answering. So you have a query, you have your question, and then you have your context. So in natural language processing, this context could be a page of text. In images, it's just an image, or in videos, it's a video. Now you want to pass each of these through their own networks. So for example, the image passes through a CNN, and your question passes through an LSTM, and so now you have some sort of embedded space. And now you want to be able to concatenate these two vectors in this embedded space, give it to another network, which figures out the answer. Well, over the last few years, people have also proposed fancier models called attention architectures. And how do these work? So essentially what you do is you say, well, the guy answering the question can't exactly extract the answer from the correct part of the image, so I'm going to do it myself. So you take your image, or you take your paragraph of text, and you break it down into words. I just use words loosely here. It's overloaded. You can think of it as patches in the image. And so now you take these image patches, and you pass each one through your neural network. And so you have an embedding for each different image patch. And similarly, you also have an embedding for the query. And so now, this is where attention comes in. Attention is basically the line in red. You want to take your query, and you want to find the most relevant part of the image, which helps you answer the query. Once you find this, once you find the most relevant part of the image, you want to again combine all of these things linearly to form an embedding of the image. But now the embedding of the image is conditional on the question that you had asked. And so now this question-dependent image embedding and question embedding are combined, and now the neural network has a much easier time to answer the question. So how do you do this on diagrams? Well, so the first thing we did was, take a VQA architecture and then, implement the fanciest attention that you have in the latest research. It actually does quite poorly. And that's because, VQA, you want to answer questions like, I don't know, what is the color of the sweater of the guy presenting on stage, or what kind of laptop does he have, or what is he doing? But what you want to do in a diagram is much more fine-grained analysis. You want to be able to answer, like, what is this diagram about? Who is eating whom? Things like that. And so what gave us much better results was to say, well, we've already done this work on syntactic parsing. We've already been able to construct a diagram parse graph. Now let's translate a diagram parse graph into natural language. So for example, if I find that tiger, there's an arrow between deer and tiger, I can actually construct a sentence which says, deer is connected to tiger, and the arrow is towards the tiger. And so now if I convert my natural image to a paragraph, I can then use NLP techniques, which is attention models that I told you, to answer a question about a diagram. And so this is exactly that. You take your diagram parse graph on the left, DPG, and then you convert these to facts, assertive statements, and then you pass each of these to an LSTM. Your question and your answer choices going through the bottom. You have standard attention architectures, and then a softmax on top tells you what's the right answer. Here are some examples of things that it's doing a decent job on. For example, it can count. It can say how many stages of growth does the diagram feature, and counting is basically counting the number of times connected word appears in your context. You can also do things like what comes before second feed and so on. So what were the characteristics of the attention models that I just told you? Well, an interesting thing that almost everyone does is you do attention between your question and your image patches, and then you get attention weights. And then you use these weights to linearly combine your attention patches into a single attention vector. So what you've done is you've taken one modality and compressed it into one vector. And then you've taken your other modality, which is question, and compressed it into another vector. And then your model on top has to figure out what's going on. So early summarization is something that most attention architectures do. The second thing is, if you look at the fanciest attention architectures, they do dynamic attention. So they say, well, why should attention be done independently? I'm going to attention on the first image patch. and I'm going to condition my second attention to what I obtained in the first image patch and so on. So it's dynamic. And thirdly, it's unidirectional. So you want to take your question and attend on images. So we did some work on trying to improve these, and we found our results show something that's slightly different. First of all, we propose using what we call attention flow. So instead of early summarization of the image into one vector and the question into one vector, what we do is we take attention weights and we take raw embeddings from your image patches and feed them into a modeling layer. And now, fancier way of saying this is saying, well, why should I linearly combine my image patches with attention weights? Let me have a neural network figure this out. Second thing is our attention mechanism is memoryless. So we found that when you do dynamic attention, you start propagating attention errors. And so, and this causes a lot of difficulty during training. And thirdly, we use bidirectional attention. So we have attention from query to context as well as context to query. Here's the model that we use. The model has lots of rectangles and arrows, but it's quite simple. So this is the first part. So on the left, you pass in your context. Okay. And on the right, you pass in your query. And so now you have embeddings from your character level, your word level, and your phrase level. And then in the middle, you have your bidirectional attention. So you have attention from both directions. But now you're passing your attention vectors straight through. And you're also passing your raw embedding vectors straight through. And now your modeling layer, which is a bidirectional LSTM, has a lot more power to be able to say which context word it can use to answer the question. So we started off trying this on a natural language processing task. Folks at Stanford have released a really large data set called Squad, which is basically paragraphs from Wikipedia with questions about these paragraphs. And so I'd like to show you a live demo about this, but before that, let me show you a quick visualization. So what does our model learn? Our model learns that when the question is when, I need to look at dates. But when a question is where, I need to look at places. And when a question is who, it's probably the name of a person. And cities are cities and so on. And so work that we're doing currently at AI2 is to see how to convert this BiDAF model and apply it to diagrams as well as natural images. Can you guys hear me now? Okay. So forgive me, work is still going on creating a good demo for diagrams and images, but I'll show you something in natural language. So here I have, these are basically from Squad, which is Stanford QA, and you can choose, a paragraph, you can input your own paragraph, and you can write down your question. So let's take this. Can you guys see this clearly? Maybe now? Okay. So here's a paragraph of text, and you can write down your own question, or you can use the question given by Squad. And the model will only pick out a span in the paragraph which contains the answer. So for example, how many miles south of Edinburgh is Newcastle? And so I hope Wi-Fi is working. Okay. So you see, it's picked up exactly that this is 103 miles. You could say things like, how far is London from Newcastle, but not in miles, in kilometers. And so, it knows that when it's kilometers, it probably has to pick out the number before km, and it figures out London and Newcastle and so on. And so this demo is up on our website, and you guys can try it out. You can provide your own paragraph and own questions and see how it works. Okay, running out of time. So now what we want to do is we want to use these kinds of models on diagrams. The problem with data sets today which do visual question answering is that either the questions are quite straightforward, they're basically object detection or attribute detection questions, or if the questions are complicated, the knowledge is unbounded. So for example, does this man have 20/20 vision, right? So you need to understand what is 20/20 vision and what that has to do with anything. And so this is quite a challenging task, I feel. So to make it a much more compact, closed world task, we propose the task of textbook QA. So we have 1,000 topics, all from middle school science, earth science, physical science, life science. Each one has a bunch of text, bunch of diagrams. Some of them are natural images as well. And then we have questions in text and diagram form. And so this is the task that we call multimodal machine comprehension. And the questions that we have aren't simple. Some of them require complex reasoning. Some of them require rich diagram parsing. Some are hypotheticals. Some require you to understand orders of events and so on. And I'd just like to advertise a challenge that we have at CVPR 2017, where we're making this data set available, and we're inviting people in computer vision and natural language processing to work on this challenge. Yeah. So the last 2 minutes that I have, I'm going to spend, very quickly try to show you a demo that I have here, as well as tell you a little bit about work at AI2 in natural images. So my colleagues at AI2 are very interested in understanding the physics of a scene. For example, on the left, there's something dynamic going on. There's people pushing a car. So if I drew a box around the car, would you be able to predict where this box moves? Well, yeah, this box is probably going to move to the left, and that ball is going to go in the air, and that kid is going to, go down because of gravity. Another thing that they are interested in saying is, well, if I have static objects, so I have a glass on the table, if I push it towards the right, where's it going to go? Well, it's going to go towards the center of the table. If I push it towards the left, it's going to fall down. What about the chair? If I push it to the right, it's not going to go anywhere because there's a wall. So how do you do this? Well, there's a spectrum of approaches you can take. One, you can say, well, CNNs are so great, let's just throw it at the CNN, let it figure everything out. On the other end of the spectrum is to say, I'm going to do very fine-grained analysis, I'm going to code up all these equations, and I'm going to take years and years to solve this. Well, the approach that my colleagues have taken uses game engines. And so you see, game engines already have a lot of physics encoded in them. And so, without going into too many details, they use game engines as intermediate representations. And so now, if you have a video of something happening, if you can find out, a scenario in a game engine which has similar characteristics, then you should be able to transfer the physics from game engine world into natural image world. And so now they can do things like, they can predict that the car goes to the left, and they can, predict that the ball goes towards the goal, and so on. Just to set up my demo, maybe you guys can switch to the phone. Basically, the last part of my, and also if it would be possible to switch on the lights, that would be good. Any chance to switch on the lights in the room? Okay, thank you. So, convolutional neural networks are great, and they work really well, but what's one big problem with CNNs? Well, they're extremely expensive to run and extremely expensive to train. So you have, you require a GPU, and even a network which was large in its day, but today is considered a small network, which is, maybe I'll close this for a second. A network which is large in the day, which was AlexNet, takes a lot of memory and a lot of time. And so what my colleagues at AI2 have been able to do is to convert these networks to binary neural nets without much loss of accuracy. So what I'd like to show you here is AlexNet, which typically runs at 3 frames per second on like a computer desktop, running at more than 20 frames per second on an iPhone using only the CPU and no connection to the cloud. So as you can see, it starts detecting people here. It's completely only on the CPU, starts in laptop, keyboard, maybe it'll get the bottle, gets the bottle. And this is not using any sort of temporal information between them. I don't think Mike is part of, maybe it thinks it's, you can get chairs and so on. Gets a wine glass, that's pretty good. And so this is on 80 categories. It's processing frame by frame independently. And like I said, it's all on CPU. So if any of you want to play with this, you can come and catch me after the talk. I guess I don't want to connect back, so I'll show you. Thank you to all my collaborators at AI2. And
okay, Annie, thank you very much. You ran out of time.
Okay. So, sure, come catch me later with questions. Yeah.